Hello, everyone. Let's get started. Um, in our last video, we discussed some of the important stuffs you must remember from your tensile testing. In that, we discuss what is actually the difference between the small strain and large strains. Why do we need to study the continuum mechanics in this format? So, without following your previous strength of material, right? It's kind of a motivation to study the continuum mechanics. Okay, so in this video, formally, finally, we are going to start our continuum mechanics. So in this case, first I am going to start the strain. First of all, you must understand the meaning of strain. Strain, it is nothing to do with the material property. Okay. Again, there's a misconception. The people think that stress and strain actually depends with the material property. No. Okay. The stress is nothing to do with the force because stress is as a result of kinematics. What we define as a kinematics. So some other place I already told you the meaning of kinematics. Kinematics mean we study the deformation without considering the forces. Okay. Therefore, strain is purely geometrical change of this material because of the deformation. Okay. Right. So then another thing is called stress. Again, the stress also not depends with the material property. The stress result of the force you are applying to the material. The force is independent with material property. The deformation also independent with material property. So now we are going to connect these two using a material property. So we can calculate separately strain and separately the stress. Then finally we are connecting these two. You may ask me the questions. What is actually you studied here? This one. So this is strain, this is stress, this is simple elasticity problem, right? Again, this equation only for the particular material. What is the material you assume? Elasticity. The simple elasticity model is this one. Here, the strain and stress, we connect with this property, right? So that is your Young's modulus. Okay, right. So we are not going to discuss this simple model here. Then here we are going to generalize, right? In the other things, there is a famous theory. Actually, it is called uh, implicit theory. Right? This theory actually developed by Professor Rajagopal. Then actually the professor has passed away uh, in last year. Uh, for me, according to myself, right, as far as I am concerned, after Newton, okay, after the Newton, in terms of the mechanics, especially in the continuum mechanics, I consider myself, I consider, as far as my concern, Dr. Rajav Gopal is the one of the best, okay, because he uh, developed a model by looking at the problem in completely different ways. Based on that, he came up with its implicit model. So implicit model means you calculate strain and separately, stress separately. We are implicitly connect these two using uh, some of the different model, right? Okay. Uh, so I cannot teach that model now because uh, you have to understand many basic things before that. But let's see if I have a time, I can discuss those theory here. But again, for that I need to have enough support because I have to put a lot of effort to explain those things. It is not a simple things, right? Okay. So here, initially I try to focus on the simplified version, then based on that we will develop. Okay. So for this, let me bring one of the picture, right? Actually, I already developed this picture. Let me bring this one here. Okay. This is I develop in Mathematica, right? So I teach one of the software, right? So it is good for symbolic calculation and metric manipulation, everything. Uh, it is called Mathematica because it is good for symbolic things. MATLAB and Python is good for the numerical stuff, right? But Mathematica, it's especially it's very nice for continuum mechanics people who are dealing with. Okay, first of all, try to understand this figure, right? In this figure, actually, uh, there are two things. First, you have to consider I shaded the outside, right? So this is actually the material, right? This one is my material. So inside the material, I have considered the, I can say it's like kind of a control volume, right? So this is the control volume, right? Okay. So this is my control volume. In this control volume, it was in one location before deformation, right? After deformation, what happened? The previously the material point was here. The same material, it moved to the different location now. Okay, so it moved to the different location. Also, there may be certain deformation in that body. It increase in size. In this case, I have drawn in such a way, right? It can reduce also, right? But in this case, I have drawn it's increased the size. Okay. So now again here I am considering why this deformation happens. Many reason, right? Because somebody has applied the load, anything, right? Some internal changes, any reason. But here we are going to study this deformation without considering the force, the magnitude of the force and everything, right? That's what we are going to do here. Right. I got an important call. I don't know where did I stop, post my recording. Okay. Uh, so bear with me if I repeat something previously I discussed in this video. Uh, then as I told earlier, here we considered without force, just the deformation without considering the force. In this case, the part before the deformation take place, this configuration we called as reference configuration. Okay, it is called as reference configuration. Okay, right. Then the current position, that means after deformation it came to this point, right? So this is called current configuration. Okay, so this is difference configuration, current configuration. Here I followed certain sign convention, right? In both configuration, I'm going to measure with the fixed coordinate frame. Sometime we can measure the reference configuration in one coordinate frame, current configuration another coordinate frame. So finally we can connect these two by interconnect the two different coordinate system. Then we already discussed, right? How can we change the coordinate system? Through the rotation, translation, right? Bar coordinate, unbar coordinate, these things already we studied in our math preliminary, right? So therefore, don't raise the question, how can we do the problem when you have two different coordinate system? Everything we studied, right? But in this case, I'm trying to explain the both configuration we connect with a single frame of reference. Okay. Again, sometime people get confused the reference code configuration with frame of reference. These two different. Frame of reference mean the coordinate axis I am considering, right? So this is frame of reference. Okay. So these two is the configuration. Okay. So then I am considering one point here. This point before deformation, this point was here. After deformation, that point will be somewhere here, right? Again, the coordinate of this point in current configuration, I mark as capital X. Capital X is the vector here. Okay, right. Then the coordinate of the corresponding point after deformation, the position vector of that point, it's small x. Again, small x is the vector. Okay, whatever I use uppercase letter, that is to represent the reference configuration. Whatever I'm going to use the lowercase letter, that represent the current configuration. Apart from that, we have something called the displacement of this point now and after, right? So this is we can represent by u. Okay, vector u, small u, right? So this is one point. The reference configuration I represent by capital B. The current configuration I represent by small b. Okay, right. Apart from that, very important things. I am considering uh, one small uh, segment, line segment here. So that is, you see, I use the capital letter DS. D capital S, right? So capital S mean to represent the line segment, the length of the line segment in reference configuration. The same line, now it is extended, right? It's deformed in different shapes, right? So now I consider this one small ds, right? The previous one is capital DS, now small s. So this is small s, this is capital S, right? Okay, right. Right. So also, again, I am saying this is within the material, right? So in this material, I consider one control volume. This volume in before and after, right? Okay. Again, so here, the whatever the point inside the reference configuration, each point represent a material point. Okay. The point inside this reference configuration, that is we called as uh, material, the points inside this this volume, that different configuration we called as material or reference. Okay, There are many names, right? Material or reference. Sometimes they called as Lagrangian, right? Lagrangian. Lagrangian coordinates. Okay. Similarly, the material points in current configuration they called spatial, right? Spatial or current, and the word Euler coordinates, right? Euler coordinates, right? Okay. Euler coordinates mean we can represent the deformation in terms of this. That means small x vector. Okay. Or we can represent the deformation in terms of this reference configuration. That means in terms of capital X. Again, sometimes people confuse with these coordinates with the frame of reference. No, both we measured one frame of reference. Only different I am talking about in the deformation equation, final equation, one can represent in terms of this uppercase X, that means material points in the reference configuration, or someone can represent the deformation in the material configuration. That means current coordinates point small x. Okay, this is very important things, right? You must understand first of all this one. Okay, right. These are first things you must understand, right? So now, from our previous math preliminary, I'm going to use the following things, right? Okay, first one, I'm going to represent uh, the points. That means capital X, right? Capital X is the vector. So therefore, uh, I will use xk. Okay, xk mean it's a vector, right? So what is actually xk? So that means the point. Okay, I will write it this way. X vector x, that is actually the point on the current configuration into the uh, uh, corresponding this one, right? The base vector, right? Okay. Again, to represent the uh, reference configuration, I use uppercase K, that means capital K, right? Similarly, I can represent this vector. Okay, so this is actually uh, xk, small k now, right? Ek, right? Okay, I'll use k, you can identify the difference, right? No issue. If I use I, it will be more. Okay, no issue, no issue. I'll use small k and capital K, right? Okay. So this is one thing, right? Okay. So now, uh, what is actually this capital K? This capital K, it depends on two things, right? One is, so that means this vector, right? Mean if I represent this one in the function form, this vector, it is depends on two things, right? One is the coordinate, the point position, right? Capital K. Another one is the time, right? Okay. So we consider the time also, right? So this vector, it is actually function of the geometry and the time. Similarly, this one also, It is a function of position and the time. Okay. So this is two things, right? This is one of the important things. Now, what I'm going to do, I'm going to connect this one with, uh, I'm going to connect these two, the variation, right? Okay. So now, if you want to find the, how can I say, the derivatives? When I find the derivatives, you see here, x also changing, small x also changing, right? So one, what you can do, you can connect the small x and capital X, right? So that means reference configuration and current configuration we are going to connect. How are you going to connect? For this one, we use the chain rule, right? Our differentiation chain rule only we are going to use here. How we are going to use chain rule? For example, if you want to apply this chain rule in multivariable calculus, you list out the variable in this way, right? This is the way I followed. Actually, I studied, right? So I cannot say I followed. Then I studied it. Most of the people, they follow the same things, right? The first, you represent the dependent variable here. First, you have to list out dependent variables. Then you have to list out the intermediate variable. Okay. So then finally, you have to list out independent variable. Okay. So this is the way, right? So now what we can do, first, this dependent variable, independent variable, it connect with the intermediate variable. The intermediate variable connect with the dependent variable. So how many independent, for example, if you have two more than one independent variable, then each this independent variable can connect with intermediate variable, right? Okay. Okay, like this. For example, I'll take the first one only, right? Right? So then this one, it's connect with your dependent variable. Okay. So therefore, how many derivatives you have to write here? One, two derivative, three derivative, and one derivative here. Okay. So this is the way normally we have to write the derivatives. So for example, in this case, okay. So in this case, we don't have independent intermediate variable because intermediate variable sometimes you can have time, right? Okay. If we consider one particular time is a constant, right? Okay. So time also you can consider, right? Right. One time is a constant, right? One particular time. So time can be, you can consider like independent variable, right? Time. Okay, I'll do it like this. Okay, time is an independent variable. This time in connect with your small x. Then let's say the capital X, right? So, so for example, can I, if someone can ask, can't I take this capital X as a intermediate variable? You can, right? Here I have a choice, right? Okay, so here my objective, what is my objective? In this case, I am going to represent my entire equation in terms of reference configuration because my final output is a reference configuration, right? That is a dependent variable. So in this case, I'm going to use Lagrangian coordinates, right? Someone can use the Euler coordinates, right? So that means small x here, right? Okay, so here, so first you have to come to here. From here, you will come to here, right? Okay, right. So in this case, how many x you have? Let's say x1, x2, x3, right? So here you have capital X1, capital X2, capital X3, right? Now you see this, let's take one X1, right? This X1, okay. So forget about the time for the moment, right? Time is connected with these two. Okay, I will write the time also, right? Only one time, particular time, it connect with these three, right? Okay. So now each X1, X2, X3 can connect with these three, right? Okay. So for example, how can I write my chain rule from here? For example, if someone has to write D, uh, this one, right? For example, uh, let's say someone has to write this one, right? This the dx. Okay, I will. Okay, my final, right? So I will write this way, right? I will write. So I will follow the books, right? The most of the books they are using. They take this is x, right? So that means I'll put this is small x, this is capital X, right? In that case, they select other way, right? Most of the case, right? Okay. So I can write that way also, but better I follow with the books, right? Books normally they keep X as a dependent variable because they they prefer the Euler coordinates, right? Because coach is stress and everything. The stress tensor you studied, that is actually current configuration, right? Okay. But personally, I like the reference configuration one. I'll tell you why later, not now, right? Okay. So for example, if someone has to find this one, right? So that means dx1 dt. Okay. So if someone has to find this one, he cannot find directly because in this case, I can write this way, but because of time is only one variable, I can write it this way, right? Okay. It's a normal differentiation, right? Rather than partial differentiation, right? Okay. So in this case, someone has to find this one. He cannot find directly because we have an intermediate variable, right? Then what we will do? First, you have to find this one, right? Dou x1 over dou capital X1, right? Plus, then, then this x1, now this x1 connect with t, right? So therefore, d, so you can write this one, right? dx1 dt. Okay. Here I'm using uh, uh, this normal differentiation here because time is the only one variable here. That's what, right? Plus, why plus? Because it connect with 3, right? So that's what I use this diagram here. Similarly, dou x1, now I connect with x2, right? x2. So now this one dx1 dt, right? Okay. Plus the last one, right? Okay. So last one, dou x1, dou x1, small x1, right? Okay. Dou x1, it's dou x3 dx3 dt. Okay. Right. So this is actually the chain rule, right? Okay. So for example, dt, I can dt is everywhere, right? If I cancel dt, I consider only the position, this one, right? Position this one. Okay, I'll keep it like this, right? No need to confuse you. Okay, yeah. or else I follow the books, right? Okay, so now if I eliminate the time effect for the moment, because time slate I can include, right? So time is not a problem, right? dt. So that means here you can write dx1, it is dou, okay, dou x1, dou cabel x1, here dx1, right? Similarly, dou x1, dou capital X2, dx uh, dx2, right? Plus dou x3, so dou x1, right? Dou small x1, dou capital X3, dx3. Okay. Similarly, this is only I have written for x1. The same thing I can write for x2, right? So now, same thing I can write for x2. What the hell this? Okay. Same thing I can write for x2, right? x2. Similarly for x3. Okay. Right. Okay. So now this one will be dx3. This is x3, x3, x3. So only I'm going to change this one, right? Okay. Okay, I'll use different color because you can understand the index notation very well, right? Okay. So here, this will be for x1. Okay. So this is for x2. This is for x3. Okay. So just a chain rule I use, right? If I want to write this one in the index notation, how can I write dx small k, right? I use small k, right? Equal. Okay. So this is the free index this side, right? Left side. So right side, the same free index, right? You see, x3 means here also 3, right? Right side, same free index, right? Okay. xk, right? xk uh, over this is dx I use capital, right? Okay, this will be dou, right? Not d, dou dx I. Okay, so this is the index notation for this one, right? Okay, right. Okay, this is very important. Now, this is the one connecting these two, right? So that means if I write it, I will go to next page, right? So that means your dx vector dx small x vector, it is actually dx d capital X d capital X, right? Okay, so this is actually the connection between, that means transformation, that connection between the Lagrangian and Euler coordinate, right? Okay, so this is very important part, right? So if I write it this one, this is, again, this is the vector. Okay, so this also vector. This is already we discussed, right? Vector, you differentiate with vector, the rank will increase, right? So that means this is now second order tensor. This tensor, right? This tensor we represent by F. So this is we called as deformation gradient. Deformation gradient or deformation matrix, right? Deformation gradient. Or sometimes they will call deformation matrix. Okay. Also they called as in maths Jacobian matrix, right? So there are many names for this one, right? Okay. Right, we will do it slowly, right? Uh, so therefore, I'll stop at this point in this video. It is very important, right? Okay, before that, let me write the index notation directly, right? So how can you write this one in index notation, this matrix, right? So D, this one I'll write as small letter, that means small I. So now this is capital I, right? I'll write it capital K, right? So therefore, this matrix we can write as now these two now free index, right? So therefore, this side the same free index, right? So we can write F I K. Okay, right. So this is the index notation for deformation gradient, right? Okay. So in this video, we introduce one of the very important property for strain, first one called deformation gradient. What is actually the deformation gradient? How your reference configuration it's deformed. How deformed? How the changes of reference configuration, that means changes of current configuration with respect to the reference configuration, right? The change of okay, so I will write this one, right? The first one, right? That means change the first one is the this represent the current configuration, right? Current configuration. This first small letter, right? This is capital letter. This is represent the reference configuration. So what is actually the physical meaning? The changes of current configuration with respect to a reference configuration, right? Okay, that's actually the deformation gradient, right? Okay. Um, okay, there are many things coming my mind. Okay, let me discuss in that video, next video, right? Okay. Again, if you do not subscribe my video, please subscribe because hereafter we are going to discuss very detailed part, right? Something you have not studied in your strength of material. That's what we are going to discuss here. Um, Therefore, if you do not subscribe my video channel, please subscribe, like the video, and share with your circle, right? So see you in next video.